Hello. So we were talking about the kerma and absorbed dose, the relationship between kerma and absorbed dose, and the difference between them. فإذا الانترفيس في إلى كتير تأثير على الريزلت، في إلى effect. الانترفيس between tissues with different densities. الانترفيس between tissues with different compositions. At this interface, the energy deposition pattern can change. This change in kerma at the interface, the change in kerma is due to the difference in mass energy transfer coefficients between the two materials. فإذا الماس energy transfer coefficient هو سبب ال changes in kerma at the interfaces. Absorbed dose, however, changes more gradually as secondary electrons can penetrate a short distance into the adjacent tissue before depositing the energy. So secondary electrons can penetrate a short distance into the adjacent tissue before depositing their energy. لهيك الابسورب dose changes more gradually. بينما بالنسبة للكيرما في عندي abrupt change. This abrupt change in kerma at the interface is due to this difference in mass energy transfer coefficient between the two regions or the two materials. So electron range, when I say electron range, هنحكي عن electrons released by photons. In diagnostic radiology, these electrons have short ranges in biological tissues, typically less than 1 millimeter, as I said here. So we can see these numbers in the table, in this table. We can see the relationship between the electron energy. إذا كان عندي electron energy 10 kilo electron volt, 20, 50, 80. We can see the range of electrons in water and in compact bone. So the ranges of electrons set in motion by photons are small in biological tissues. So all the numbers here are smaller than 1 millimeter. هنحكي ب 25 micrometer أو 15 micrometer, 51 micrometer, 0.2 millimeter, 0.5 millimeter, 0.8 millimeter. This indicates that the changes in absorbed dose at the interface between two tissues in the body are limited to small regions. The diagnostic dosimeters فعليا هني instruments designed to measure the amount of radiation absorbed by a material or a person. They play an important role in monitoring radiation exposure. هن فعليا detectors. They are used to determine the absorbed dose or kerma or their time rates. A dosimeter is composed of the detector. The detector هو the core part of the dosimeter, which interacts directly with the radiation. The detector بيقيس a dose-dependent physical property, such as charge, light, temperature. These quantities or physical properties change proportionally with the absorbed dose or kerma. فإذا الميجرمنت بيكون proportional على الابسورب دوز أو الكيرما. So a dosimeter is composed of the detector and other components which convert the detector signal to the absorbed dose or kerma value. The measurements necessary for dosimetry include X-ray tube output determination. So dosimeters measure the output of the X-ray tubes in diagnostic radiology to ensure the delivered radiation is within safe and effective limits. Also, we can also includes the patient dosimetry. So dosimeter أكيد فينا نستعملهم to measure the incident air kerma or the entrance air kerma, which quantifies the radiation dose received by the skin at the point of entry. The patient dosimetry helps in calculating the kerma area product, KAP, kerma area product, which is the total radiation dose multiplied by the irradiated area. Also the internal organ doses through modeling. Dosimeters كمان فينا نحكي كمان عن measurements like the control of doses to staff, so we can monitor the staff dose. This is to protect the healthcare workers by monitoring radiation exposure in medical facilities. So the control of doses to staff through area and individual monitoring. So staff dose monitoring includes area monitoring to measure environmental radiation levels and individual monitoring to track personal radiation exposure. DCPE, in the previous chapters, I introduced the CPE, the charged particle equilibrium in dosimetry. هنحكي هلا عنه أكثر. Charged particle equilibrium, CPE. It occurs in a material when the number of charged particles entering a small volume is equal to the number of charged particles leaving that volume. لهيك بنحكي هون بإكوليبريوم. So equilibrium دائما بالاكوليبريوم ستيت الانبوت numbers بيساوي الاوتبوت numbers. In dosimetry هنحكي عن number of charged particles entering a small volume number of charged particles leaving that volume. فإذا إذا كانوا مثل بعض بنحكي عن charged particle equilibrium أو CPE condition. So CPE is an essential concept in dosimetry. It allows for accurate calculation of absorbed dose or kerma. How it is achieved when a beam of uncharged particles, يعني هنحكي عن photons ونيوترونز مثلا. When a beam of uncharged particles, ionizing particles, irradiates a homogeneous material, the radiation field transforms into a combination of the following, a mixture of the following: the incident beam, يعني هنحكي primary radiation, the initial uncharged ionizing particles that penetrate the material. هذا الانسيدنت beam. The incident beam is attenuated by the material, is reduced by the material. So it is attenuated, it is reduced as it interacts with the material. كمان في عنا scattered radiation. Scattered radiation هنحكي ب secondary radiations. هدول secondary radiations are produced when the incident beam interacts with the atoms in the material. So this includes scattered photons and other particles. في عنا Brimstolling radiation. So كمان حكينا عنها بشكل مفصل. Here the X-rays generated when high energy charged particles decelerate as they pass near atomic nuclei. وفي عنا charged particles فينا نحكي عن secondary particles liberated directly by the interaction of the uncharged radiation. وفينا نحكي عن electrons set in motion, and the electrons set in motion by these secondary particles. فإذا ال CPE is important. لهدول is important. هلا أكيد ال CPE يعني فينا نحكي مثلا أو فينا نشتغل على ال calculation of absorbed dose or kerma. So determining the absorbed dose requires knowledge of energy deposition by secondary charged particles. However, this is challenging because the radiation field is complex. The CPE simplifies the calculation. So simplifies the calculation of the absorbed dose or kerma. Because the energy deposited in a volume equals the energy carried into the volume by the secondary particles, if CPE exists. So the accurate description of the components of the radiation field in a volume where absorbed dose or kerma are to be determined cannot be done with analytical methods. هلا هون we need a numerical method. يعني it's too difficult to accurately describe the radiation field components analytically. ليه؟ لأن في عنا complexity كتير كبيرة. يعني ال interaction process is very large. The interaction process is very complicated. So CPE is assumed, or numerical methods like Monte Carlo simulations are used to model these interactions. في عنا موديل اسمه Monte Carlo simulation. Monte Carlo simulation model. عن طريقه ممكن نعمل estimation لل components أو components of the radiation field. So this can be done with numerical methods or experimentally when there is equilibrium of charged particles in the volume. يعني يا إما بدنا نشتغل على موديل على مونتي كارلو سيموليشن موديل كتير معروف بيتعامل مع random variables. هلا هون فيني اعتبر الفوتونز هن الراندوم particles. بدنا نشوف كل فوتون شو حيصير فيها بقلب الانفايرمنت بقلب الماتيريال وان interact with the material. يا بدنا نستعمل مونتي كارلو سيموليشن لحتى فعلا نشوف شو حيصير بالانتراكشن، او we can assume CPE, can assume that we have an equilibrium of charged particles in the volume. So when these ionizing radiations, when these photons interact with the material, it can liberate electrons from atoms. This will create electron tracks, what's called electron tracks. These tracks are essentially a path of ionized atoms and the free electrons left behind by the interaction. So tracks هني essential path of ionized atoms and the free electrons left behind by the interaction. A number of tracks is small near the surface of the material and increases as you go deeper. So here in this figure, in this figure we explain we can see that here in the first figure the geometry of a material. This is the material. The geometry of the material irradiated from here, from the left, with a mono-energetic beam of photons. هذا المونو-energetic beam عنده energy E equal H mu. This is the energy of the mono-energetic beam of photons. Of course, the photons في عندهم energy. As these photons travel deeper into the material, they are more likely to interact with atoms and transfer their energy. So this can result in the liberation of more electrons and the creation of additional electron tracks. So the deeper the material, the more interactions are possible. This will lead to an increase in the number of tracks. So here, the tracks of the charged particles liberated in the material are shown. فينا نشوف إنه directions are the same. So here the assumption is that all electrons liberated have the same direction, the same energy, and they have a straight track. So we can work with at a specific, we consider a specific volume on the surface. نحن المفترض نشتغل على specific volume على volume معين and we can obtain we can make the conclusions. فإذا near the surface of the material, the number of electron tracks crossing a volume dV, this specific volume, this small volume, so number of electrons, number of electron tracks crossing the volume is, of course, is small, as fewer photon interactions have occurred. As the depth increases, more electrons are liberated due to the photon interactions, and the number of electron tracks in dV increases. So the number of electron tracks which crosses dV is small near the surface of the material, but increases as the volume moves to a greater depth, because more electrons are liberated by photon interactions. So as the electron path have finite length, finite ranges in the material, the number of tracks reaches a maximum at a particular position of dV, and eventually begins to decrease as the beam is attenuated for greater depth. فإذا electrons have finite ranges in the material, meaning they cannot travel indefinitely. This causes the number of tracks to reach a maximum at a certain depth, where the combination of photon interactions and electron energy ranges is optimal. So at deeper level, at deeper attenuations, the photon beam becomes attenuated, يعني بيخسر intensity بشكل كتير كبير. So it becomes attenuated as it transfers energy to the material. This will reduce the number of liberated electrons and consequently reducing the number of electron tracks. The total path length of charged particles in each volume represents the number of ionizations that occurs in the volume. So the total path length of charged particles within each volume dV correlates directly to the number of ionizations in the volume. This total path length is a critical factor to determine the absorbed dose or energy deposition in the dosimetry. فإذا بس يفوتوا الفوتونز على الماتيريال ويعملوا interaction مع الماتيريال, distribution of charged particles and ionization changes with depth. أكيد they change with depth to the they change with depth. هيصير في عندي تغيير مع الدبث. أكيد هيدا الشيء لازم حنحكي عنه أكتر. هلا حنشوف كيف يعني changes، شو هن، كيف بيصغر، كيف بيصير في عندي attenuation. السي بي اي فينا نميز هون بين شغلتين، بين تو بروسيسز يلي هن سي بي اي اند تي سي بي اي. فاذا يعني فيني احكي عن charged particle equilibrium و transient charged particle equilibrium. فاذا السي بي اي والتي سي بي اي refer to different stages in the interaction of charged particles with the medium. شو الفرق بيناتهم؟ بالنسبه للcharged particle equilibrium، هذا الشيء اللي فينا نشوفه بهذه الصوره، والتي سي بي اي اللي فينا نشوفه بالصوره الثانيه. فاذا هون حنشوف التوتال ionization in volume dV per depth along the beam direction, how this is changing. فاذا السي بي اي occurs when the number of charged particles entering a specific volume within a medium is in balance with the number of charged particles exiting that volume. In CPE, the ionization chamber, for example, experiences a constant dose rate. This equilibrium stage is reached when the rate of charge deposition in the medium is balanced by the rate of charge removal. فإذا the CPE represents a balanced state where the rate of incoming and outcoming charged particles is constant. بينما the TCPE refers to the initial transient phase when the rate of ionization is fluctuating rapidly and hasn't stabilized. So بهدول الصورتين الموجودين، فإذا فينا نقارن بين two concepts: charged particle equilibrium وال transient charged particle equilibrium concepts. فينا نطلع فإذا على هيدا الدوز depth curve. فإذا عندي هون التوتال ionization، يعني عم نحكي عن الدوز depth curve كيف بيتغير. أو خلينا نشوف صورة تانية مثلا، هون بتكون أوضح. بهيدي الصورة هنشوف بالتحديد الدوز depth curve. فإذا بالفيجر، أول فيجر A، الدوز delivered per unit mass يلي هو D، this is D، rises, it increases initially due to the buildup of secondary electrons liberated by photons. لنوصل لمرحلة هون بصير في عندي stable variations، بصير في عندي equilibrium. So at CPE عم نحكي بعد هيدا ال pointed line، بس نوصل ل equilibrium state بنحكي عن charged particle equilibrium. So at CPE, the energy deposited by secondary charged particles balances the energy leaving the volume. This leads to a steady absorbed dose. بالصورة الثانية بالتي سي بي اي، in high energy photon beams beyond the depth of maximum dose، يعني بعد الزد ماكس، بعد هيدي النقطة، شو بيصير؟ في عندي transient charged particle equilibrium instead of full charged particle equilibrium, instead of full CPE. So this occurs because secondary particles مثل electrons have longer ranges, leading to a net energy loss as the beam penetrates deeper. هلا اكيد نحن هنشوف الدوز هون، الدوز كيف هيتغير مع الدبث، يعني كل ما as we go deeper, as the beam penetrates deeper، شو هيصير؟ هيصير في عندي decrease أو loss in energy. هيدا الشيء بيؤدي ل transient charged particle equilibrium. فإذا بأول بارت من الصورة، يعني أول بارت هيدا اللاين قبله عم نحكي ب build up region in both figures, in both cases. In both cases في عندي build up region which refers to the initial depth where the dose increases as secondary particles are generated but have not yet reached the equilibrium. So this is important. أكيد بالصورة هون نحن هنحكي عن ال D وال K collision، يعني هنحكي عن ال absorbed dose وهنحكي عن بارامتر تاني اللي هو ال collision كيرما. فإذا فينا نشوف ال collision كيرما وفينا نشوف ال absorbed dose بالصورتين كيف هيتغيروا. بالنسبة للكيرما برجع بذكر الكيرما يلي هي بتعبر عن ال kinetic energy released per unit mass released by uncharged ionizing radiation in a material. بينما إذا بدي أحكي عن الكوليجن كيرما هي the fraction of K that is used for ionization and excitation, the fraction that contributes directly to the absorbed dose. So both are calculated by using these equations, K equal phi H mu. So الكيرما والكوليجن كيرما they are calculated using these equations. فإذا هون ال H mu هي الفوتون energy، الفاي الفوتون fluence، الميو تي ار over rho هي الماس energy transfer coefficient، ميو اي ان over rho هي الماس energy absorption coefficient، وبساي هي الانرجي fluence. So in radiation physics and dosimetry, the behavior of collision kerma with depth depends on how the photon fluence changes as radiation penetrates a material. So when the fluence is constant، هذا الشيء كنت بدي اقوله هون. فاذا اذا بدي قارن بين figure A والفيجر B، هلا اكيد total ionization inside a volume dV as function of the depth of the volume in the material. هيدا الشيء اللي هنشوفه بالصورتين، ولكن عندي two cases. بأول case الفوتون fluence is constant، بتاني case الفوتون beam is attenuated as it enters the material. فإذا أول state، هلا أول state فيني سميها ال state of constant ionization، كمان فيني سميها charged particle equilibrium state. Because in this situation the charged particles which are liberated in the volume dV and leave the volume are balanced in energy and in number. بينما بتاني case نحكي عن expectation value of the total ionization in volume dV. The expectation value increases initially but then decreases slowly with increasing the depth in the medium. At depth beyond the maximum of ionization، بعد الماكسيموم بس نوصل على الماكسيموم ببلش يصير في عندي decrease. هون هيدي الستيت بسميها TCPE as we can see also in this figure. So بعد الماكسيموم Z max فينا نشوف slight decrease in the dose. So الcollision kerma will absorb dose as function of depth in a medium فينا نشوف هون بهدول الصورتين. هلا if the in this scenario so K collision increases in the build-up region. K collision increases in the build-up region as the number of secondary charged particles grows, reaching a maximum at a certain depth where CPE is achieved. Beyond this depth, K collision remains constant because the fluence doesn't decrease significantly. Now, when the fluence decreases exponentially, so here it is usually it is considered that the fluence decreases exponentially with depth in the material. When the photon fluence decreases exponentially with depth due to attenuation, of course, the behavior of K collision mirrors this exponential decrease. كمان فينا نشوف ال K collision how it is decreasing. So بالbuild up region, K collision initially increases as secondary charged particles are generated. After reaching a maximum at depth Z max, the collision starts to decline exponentially. Of course, following the behavior of the decreasing fluence. So this is the build up region. فإذا بهيدا المنطقة قبل الزد ماكس، قبل ما نوصل على الزد ماكس في عندي البيلد اب region for the dose at small depth in the medium. The build up region has dimensions similar to the range of the charged particles in the medium. The absorbed dose D depends on the deposition of energy by charged particles. It is smaller at the surface of the material than inside it. أكيد inside the material D, the absorbed dose is increasing. In both cases يعني بهيدي الكيس يعني عم نحكي بالبيلد اب ريجن بشكل عام. So beyond the build up region يعني عم نحكي هلا بالجزء الثاني. A relation between absorbed dose and collision kerma could be expressed in this way. D equal K collision. طبعا هون بالسي بي اي هيدا بالcharged particle equilibrium state. فإذا بالسي بي اي D equal K collision. So equal phi H mu E N over rho. So there is a coincidence of absorbed dose and the collision kerma as true charged particle equilibrium is achieved. So here the assumption is that the changes in photon fluence are small and the volume of interest has small dimensions compared to the electron range. So in this case, D equal K collision. في عندي coincidence بين الabsorbed dose والcollision kerma. Now, when the attenuation of the photon beam is not negligible beyond the maximum, the absorbed dose is larger than the collision kerma. The absorbed dose in this case إذا في عنا attenuation للphoton beam, when the attenuation is not negligible, so the absorbed dose is larger than the collision kerma. يعني the absorbed dose is different than the collision kerma. As the energy imparted is due to charges liberated by photon fluences, slightly larger than the fluence in the volume of interest. So absorbed dose والcollision kerma ما بيساووا بعض. فيني we can express the relationship between the absorbed dose and collision kerma using this relation D equal beta K collision أو beta equal D over K collision. So إذا بنطلع على الرسم بنشوف at Z max beta is equal to 1. ليه؟ لأنه هون الدوز absorbed dose والcollision kerma are coincidence بيساووا بعض. قبل الزد ماكس يعني at smaller depth in medium beta is negative. After Z max beta is positive. So D and K collision are different. And D, the absorbed dose is larger than the collision kerma.